What if you were right, but almost nobody understood you? What if your idea challenged one of the greatest scientists in history? And what if the only way to prove it was to wait for the sun to disappear? In 1919, Albert Einstein faced one of the most dramatic tests in the history of science. For years, he had been telling the world something almost impossible to believe. Gravity, he said, was not simply a force pulling objects together. Gravity was the bending of space and time itself. To ordinary people, this sounded strange. To many scientists, it sounded almost too bold. Because Einstein was not just adding a small detail to physics, he was challenging the universe described by Isaac Newton. And Newton had ruled science for more than 200 years. Newton's theory of gravity had explained falling apples, orbiting planets, and the motion of the moon. It worked. It was beautiful. It was powerful. So when Einstein came along and said, there is something deeper, people had a reason to doubt him. Not because Einstein was foolish, but because Newton was a giant. And if you want to challenge a giant, you need more than a brilliant idea. You need proof. Einstein's problem was simple. His theory was too difficult for most people to understand. He was talking about space bending, time changing, light following curved paths. These were not things people could touch or see. You could not hold curved space-time in your hand. You could not look out your window and say, there it is. So Einstein needed something visible, something measurable, something the world could not easily ignore. And his theory gave him exactly that, a prediction. Einstein's theory said that if light from a distant star passed close to the sun's gravity would bend that light. That meant the star would appear to be in a slightly different position in the sky. The star itself would not move, but its light would curve as it passed near the sun. This was the key. If the light bent exactly as Einstein predicted, then his theory would pass a powerful test. But if the light did not bend that way, then general relativity could fail, and Einstein's great idea might become just another beautiful theory that nature refused to obey. But there was a problem. How do you photograph stars next to the sun? Normally, you cannot. The sun is too bright, its light overwhelms the sky. Even if stars are behind it, you cannot see them. But there is one rare moment when the sun becomes dark enough, a total solar eclipse. When the moon passes directly in front of the sun, daylight fades. For a few minutes, the stars near the sun can appear. And in those few minutes, scientists could take photographs. They could compare the stars' apparent positions during the eclipse with their normal positions later. If those tiny points of light had shifted, Einstein might be right. On May 29, 1919, the opportunity came. A total solar eclipse would pass across parts of the Earth. British astronomer Arthur Eddington helped lead an expedition to the island of Principe, off the west coast of Africa. Another team traveled to Sobral, Brazil. Their mission sounded simple: photograph the stars during the eclipse. But in reality, everything depended on a few fragile minutes. The weather had to cooperate. The telescopes had to work. The photographic plates had to capture the stars clearly. The measurements had to be precise. And the result would decide whether Einstein's strange theory had touched the truth. Then came the tension. In Principe, clouds filled the sky. Imagine traveling across the world with heavy equipment, waiting for one rare eclipse, only to see clouds covering the very sky you came to study. There would be no second chance the next day, no pause button, no retake. The eclipse would come and go whether the scientists were ready or not. As the moon began to cover the sun, the light faded, the sky darkened, the temperature dropped. And through breaks in the clouds, Eddington's team tried to take the photographs that could change physics forever. For those few minutes, the entire story of modern physics seemed to hang in the darkness. Would the stars appear where Newton's theory expected? Or would they appear where Einstein's theory predicted? The answer was hidden in tiny dots of light on photographic plates. After the eclipse, the photographs had to be measured carefully. This was not a dramatic explosion. There was no machine lighting up with a final answer. It was slow, precise, difficult. The scientists had to compare the star positions from the eclipse with reference photographs of the same stars taken when the sun was not nearby. The difference was extremely small, but that small difference mattered. Because Einstein had predicted a specific amount of bending, not just light will bend, but how much it should bend. That is what made the theory scientific. It could be tested, it could be wrong. And that is why the 1919 eclipse mattered so much. Then, in November 1919, the results were announced. The measurements supported Einstein's prediction. The light from distant stars had appeared to bend around the sun. And suddenly, the world changed. Newspapers began printing dramatic headlines. Einstein became famous almost overnight. Before this moment, he was respected by scientists, but not known by the general public. After this moment, he became the face of genius. A man with wild hair, a man who had seen something hidden in the universe, a man who seemed to have proved that space and time were not what humans had always imagined. But here is the most important part. Most people still did not understand relativity. They did not suddenly understand the mathematics. They did not suddenly understand curved space-time. But they understood the story. Einstein had made a bold prediction. Scientists had traveled across the world to test it. The sky had been photographed, the measurements had come back, and the universe seemed to say, Einstein was right. This is why 1919 was so powerful. Einstein did not convince the world by explaining his theory more loudly. He did not win because he was popular. He did not win because people wanted Newton to be wrong. He won because his theory made a prediction that reality could check, and reality appeared to confirm it. That is the heart of science. A scientific idea must be brave enough to face evidence. It must be able to say, if I am wrong, the universe can prove me wrong. Einstein's theory took that risk, and in 1919, during a solar eclipse, it survived. But this does not mean Newton was useless. That is a common misunderstanding. Newton was not simply thrown away. His laws still work incredibly well for everyday life. They help explain falling objects, moving vehicles, bridges, machines, and much of ordinary engineering. But Einstein showed that Newton's picture was not the full picture. Newton described gravity as a force. Einstein revealed something deeper. Massive objects bend space-time, and light follows the shape of that curved space-time. The sun was not grabbing light like a hand. It was bending the road that light traveled on. That idea changed physics forever. Today, general relativity helps us understand things Einstein himself never saw directly. Black holes, gravitational lensing, the expansion of the universe, even the tiny time corrections needed for GPS satellites. That means Einstein's theory is not just an old story from a science textbook. It became part of how we understand the universe. But the moment that brought it into the public imagination came in 1919. Not from a classroom, not from a speech, not from a formula on a board, but from an eclipse. For a few minutes, the moon covered the sun, and in that darkness, scientists saw the stars in a new way. That is why this story is not just about physics, it is about belief. How does the world begin to believe a new idea? Not just because someone intelligent says it, not just because the idea sounds beautiful, but because the idea takes a risk. It steps into the real world and allows itself to be tested. Einstein's theory did that. It predicted that starlight would bend near the sun. And during the eclipse of 1919, the evidence supported him. That was the turning point. A theory that many people could not understand became a headline the whole world could feel. So when we say Einstein proved relativity was right, we should understand what that really means. It does not mean one eclipse answered every possible question forever. Science is always tested again and again, but in 1919, Einstein's theory passed one of its most famous tests. It made a strange prediction. The world waited. The sun disappeared. The stars appeared, and their light bent in the way Einstein had predicted. That was enough to transform him from a brilliant scientist into a global legend. Before 1919, many people heard Einstein's theory and thought it was too strange to believe. After 1919, they still may not have understood it. But they knew one thing. Einstein had looked at the universe differently, and the universe had answered back. That is the story of the eclipse that proved Einstein right. And it reminds us of one of the deepest truths in science. A great idea does not become powerful because everyone understands it immediately. It becomes powerful when reality itself begins to agree.